Hey there everyone, I hope you guys are doing well. We are going to study inductance today. And what is inductance? And another thing that inductors do is self-inductance. So we are going to study what an inductor is first, then we're gonna go ahead and learn some more details about it. First of all, an inductor is just a solenoid, and you've seen a solenoid before. A solenoid looks like this. It's a conductor, a wire that is wrapped around in a helical way, and that's what an inductor is, okay? So if we want to look into the operation of an inductor inside an electric circuit, we need to look a little bit further. So let's say we have a current going into this inductor, and this white block is drawn just to show you where the current is going. So the current is going this way up, then it goes behind, so basically it continues like that and keeps going again like that. But I just drew the block so that you can see where the current is going in and where the current is going out of the page. So this is exactly where this thing stands, okay? So the current is coming down here. There's an electric current that is going here. So this is a solenoid, and there is this current going this way. And I'm going to draw this where the current is. So the current is filling out this loop here. And the current travels at a limited speed, while the magnetic field resulting from the current travels at the speed of light. So the magnetic field flux is much faster than the speed or the velocity of the current. So basically what this is going to do is this is going to create a magnetic field. And if you use the right-hand rule, the magnetic field from this original current here that is in the first loop is going to be directed this way. So let's use the right-hand rule here just to imagine the situation better. So you grab on the coil so that the current is going looping. As I said, the current is going inside behind the block. So then my thumb will point to the magnetic field, which is to the left, and this is my left. So the magnetic field, the original magnetic field, is going to be this way, and that's what we found here. So I'm going to call this B, okay? Now what's going to happen, there's a magnetic field growing because of there's current in this loop within the vicinity in the second loop. So let's call this 1. I'm going to call this 2. Okay, so loop number 2 does not like this change. According to Lenz's law, it's going to create a current that opposes the change in the flux. And where's the change in the flux? This way. It's growing this way. So it's going to create its own magnetic field that is going the other direction. And if you create another magnetic field that is going the other direction, then that will reverse the current. And this process, I'm going to write it in red, is going to create a current that is going the other direction. So there is a current that is going another direction in the other loop. Now these two currents, what they're going to happen to them, they're going to meet somewhere here, okay? And they're going to kill each other. Basically, they're going to die down to zero, okay? So now there is no current. The current stops here, all right? Now, since the current stops here, then there is the magnetic field here dies. There is no change. And there's the induced magnetic field in the second loop also dies. There is no change, right? Okay, but this current has still a source, because this current probably, I'm going to assume it's connected to a battery, okay? So this current has a source. Since this current, first of all, killed the original one, okay, because of there is a magnetic field change. So they both are dead now, but this current has support from the battery, so it's going to continue now to the second loop. And again, since we have a current that is growing in the second loop, there is a magnetic field flux that has a direction this way. This loop feels it, it doesn't like it. It makes another magnetic field the other way, and it makes another current that is opposite to the direction of the original current. Here they meet somewhere around here, they kill each other, and the process repeats itself. So until it keeps repeating itself like this, until the original current, the white one here, gets there and clears the inductor and goes back to the battery. So what does the inductor do basically? The inductor delays the growth of this current. So let's say this is current I, goes here, it dies, it gets smaller, and then goes here, it dies, and it grows a little bit more, but it's still smaller than I, and so forth. So the growth of the current comes like this as time passes by. Okay? All right. So why is this important? Because this, what the solenoid does, or the inductor does, is creating what we call a back EMF. So this is called a back EMF. This back EMF does not last much. As soon as it grows and this back EMF pushes the current this way, opposite to the original current, they kill each other, it dies out, and it grows again, and it dies out, and it grows again. And this process keeps repeating itself, as I mentioned, until the current clears the inductor. And that's a very important thing in an electric circuit, because some electric circuit elements inside the circuit itself, if it sees a surge in the current, like a sudden surge in the current, that element goes bad, it burns. If you actually switch a current from 0 to 100 amps or from 0 to 50 amps, all of a sudden, sometimes some electric elements do not like that, and they burn out and they go bad. So an inductor is a very important thing in an electric circuit because it protects other electric elements in the circuit. Okay, so that's what an inductor does. All right, so now how do we find the inductance? We learned about what? The capacitance for electric field. The inductance is the same thing, but for what? A magnetic field. So let's remember, first of all, we have the electromotive force according to Faraday's law is equal to minus n, the change in the flux divided by the change in time. Let's take the absolute value of this. So I don't care if it's positive or negative. I just want to try to hand wave, kind of like derive an equation for the inductance. All right, so this delta phi over delta t, which is the change in flux with respect to time, since it's happening because of a change of current, so this whole thing can be proportional to the change in the current with respect to the change in time. Okay? All right? And this n here, which is the number of loops in a coil or something like that, can be translated into the inductance. I'm going to call it L. All right? Because the more the loops, the more the power the solenoid has, if you quote unquote, and then it was, so that's why it's proportional to L instead of N. So E, which is the electromotive force, and that's the back EMF, all right, is equal to L, the change in the current divided by the change in time. All right. Now this L is known as the inductance, and this inductance is measured in a unit called Henry, and for short it is H. Most inductors are measured in either like millihenry, microhenry. This is 10 to minus 3 Henry, and this is 10 to minus 6. So because inductor is a huge unit, so you need to down it with milli or micro to be able to measure a practical unit of it. All right, so what is inductance? Let's try to find it out. Let's take this equation and try to find a good representation of the inductance in a circuit. All right, let's look at this one here equation. We have n phi from here, okay, is proportional to the magnetic field, and the magnetic field is proportional to the current in the solenoid. Okay, all right, then n phi is proportional to I. All right, If it's proportional to I, we can change the proportionality into equal sign, and when we do that, that will be L, which is the inductance, times I. So if I want to write this equation in a better form, I should say that L is equal to N delta phi over delta I. So what this equation is telling us is that the inductance of a solenoid in a circuit is equal to the number of the solenoid loops times the change in flux when I changes. That's it. So change in flux when I changes times N is equal to L. And another good equation we need to box it is the back EMF, which is equal to L delta I over delta T. All right, now let's have an example. Okay, an inductor of 2 millihenry carries a constant current of 3 amps. If it was switched off, it induces a 7.5 back EMF, electromotive force. Find duration it takes the current to die to zero. So we have a solenoid, and there's a current inside that solenoid, all right? And this current is 3 amps. And the supply current, that is 3 amps, is switched off. We should know that the current is not going to die suddenly because this is an inductor. It's trying its best to keep the current alive. All right. So let's solve how much time it takes the current to die. Okay. So we can use this equation. We can use this equation, which is E is equal to L, the change in the current with respect to time. All right. Now we can, so to continue here, we have the back EMF that it was produced is 7.5. We don't care about if it's positive or negative because it's absolute value. Now L is also given 2 millihenry, so 2 times 10 to minus 3. Now delta I is I2 minus I1 divided by T2 minus T1, and I2, which is 0, so that's 0, minus I1 is 3, and the only unknown is the duration of time. Notice if you keep solving that, you're gonna get the answer in negative, but we don't care about the time per se. We care about the duration it takes, which is a magnitude. All right, so let's plug all of these numbers in. 7.5 divided by 2 times 10 to minus 3, okay, and also divided by 3 from this. That should be equal to 1 over delta t, which is the duration of time we're looking for. Solving for delta t, we get delta t, which is the duration of time, is equal to 8 times 10 to minus 4 seconds. Okay, a small time, but a time that will give other elements in the instrument to stay in a good shape. And that's it for this one. Thank you.